Good morning, Caleb. How are you doing?
Good morning. How are you? I'm good.
Perfect, perfect. So, how was your experience with the workshop? Did you have a chance to practice a little bit the commands
Honestly,
and installation? Yeah,
really good.
perfect.
I think at some point probably gonna go back and like go through it all again.
That's
Um,
a very good idea.
but
Yeah.
no, it's been really cool and much easier to follow than the BIOS one.
Yeah. Yeah.
Yeah.
So you have some experience with MSL. That's, I guess, helps a little bit, hopefully.
Yeah.
Yeah.
And now it's
So,
really cool because with this new one, it might be cool to like rebuild it with the new MSL 4.
yeah, in future we have to do that, I guess. Yeah. You remember this reaction rates and reaction data, everything. We can use Python, and with one line we can just we don't need that long files containing all the reaction and everything. We just
Yeah,
can add just one line and be done with it.
that'd be awesome.
Oh,
I think that's why I've been liking this workshop more because it's more applicable to me
yeah,
personally because I haven't gotten to use any of the other tools yet in the application.
perfect,
Yeah,
perfect.
it's been awesome. I like Tom a lot. I think
Yeah,
he's
Tom is
fun.
very nice and fun. Yeah. You remember Borak? Yeah.
Yes.
He's going to Tom's group hopefully soon.
Oh, cool.
Yeah, I should ask how is the um, like his application is going, but it seems that he got a job there, so we will see. Okay, yeah, yeah. I see only three people here: me, you, and Susan Mertens. How are you,
Yes,
Susan? How are you
I
doing?
know. I'm wondering where everybody is,
I mean, I don't know.
especially our speaker.
Our speaker probably, yeah. I I, I saw Jim in, I mean, not in person,
Yeah.
but in the dock. He was typing something there, so I'm
Okay.
sure.
There we go.
Yeah, he will be around very soon. I can send him a message. Yeah, he was editing the Google Doc. I was, yeah, watching. He's, typing something there. So I can send a message to everyone, maybe to presenters at least. Just give me 1 second. Or maybe I should share the Zoom link, but I guess people should know how to find it. Okay, let me check.
Good morning, everybody.
Good morning, Tom. How are you doing?
Doing very well.
Yeah.
Bright and early. We had a beautiful sunrise.
So So it's almost 10:30 here.
Yeah.
Yeah.
Morning, Adam.
Good morning, Adam.
Doing good. So there was a news report yesterday that I think the reason you were cut off yesterday, Adam, was because of a power outage. There was a brownout
Okay.
just for a few seconds.
Unfortunately, it was this short.
Yeah, yeah, right.
I know that last year I connected my computer with a wire, with an Ethernet wire, just to be sure.
Yeah, just to be sure. Yeah,
Experience any issues, so I thought, okay.
yeah, yeah.
Tom, a question. As I remember, you changed your session with Jim. Am I right?
Yeah. So Jim should be coming on here. I'm not sure where he is.
I saw him editing the portal. So
Okay, so he'll be here.
wrong, but
Yeah, I'm sure he'll be here in a second. Yeah, do I see his?
oh, okay, yeah. Jim just said that last minute coding.
Okay.
Tell them a joke. Okay, so Tom, go ahead. Start the session with a joke, if you.
Oh, start with a joke. Okay. I don't.
So anyone else who remember a joke, you can just feel free to.
Yeah, I'm not. I don't know why I'm not very good at jokes.
I mean, my jokes are not appropriate for this session.
Oh. Oh, Rosita. Rosita.
Yeah.
I didn't know that about you. Okay.
Yes.
Oh, okay.
Adam, you go ahead. Yeah.
Yeah, I found one joke here.
Okay.
Why did the biologist break up with the physicist? They had no chemistry.
They had no chemistry. Okay.
Yes. Very nice joke. Yeah. So, who else? Caleb, do you know a joke?
Definitely not. Unfortunately. The only jokes I have are dad jokes, and I don't think those are entertaining.
Uh-huh.
It
Oh,
could be.
so Adam's joke reminded me of the three statisticians who went deer hunting. So they were out deer hunting and they saw a deer, and the first statistician took a shot and it went about 10 feet too far. The arrow fell about 10 feet too far. And the second one took a shot and it fell about 10 feet too short. And the third statistician said, "We got him, we got him." And that's actually an appropriate joke for the top secret model that Jim and I have been working on for today's session. That's actually pretty appropriate. You'll see.
So, yeah.
How about somebody else?
I see Ali here. Ali, do you know a cool joke? Share with us. I know you do.
I don't, but I can try to think of one. Most of the jokes I ever know was about programming anyway.
About what?
Programming.
Programming. Yeah, that's actually good. Go
He's
ahead.
here as well.
Yeah. Oh no. I tried to look up some and they're terrible.
How?
Oh, why did the programmer quit his job? Because he didn't get a raise. As an array.
Arrays, right.
Mm-hmm.
Array. Yeah.
I'm very sorry. I'm very sorry I did this.
That's a very appropriate joke for this morning. I was trying to arrays. NumPy arrays always trip me up. I'm used to math. So.
Why are assembly programmers always soaking wet? They work below sea level. As in C programming language.
Uh-huh. Yeah.
Okay.
You got a store of these. That's pretty good.
I'm very sorry again. This is that was awful.
It's my fault. I said to tell jokes.
We took it very seriously. Jim, yeah, you should go ahead with the joke too. You were late.
I don't know any. I'm terrible.
So the one appropriate for today that I told before you got here, Jim, was about the 3 statisticians who went deer hunting.
I don't know that joke.
Oh, I'll tell it again so that you can hear it. It's
feels
appropriate.
like-
It's appropriate. It's exactly appropriate for today's presentation. So they went deer hunting, and the first statistician, they saw a deer. So the first statistician took a shot, and the arrow went 10 feet too far. And the second one took a shot, and it fell 10 feet too short. And the third statistician said, "We got him. We got him."
Exactly.
Continue like that. If you
Well,
want.
and then Mark Twain's famous, I won't have the exact words, famous statement about lies. He said there are lies, damn lies, and statistics.
That's a very good one. Yeah.
Yeah. Also appropriate for today's model.
Yeah, the model doesn't have any like definite answers.
No.
It only makes sense when like seen from an average point of view, but that's not my fault.
Yeah.
I'm just going to show people how to encode the model.
Yeah. But if you try to make sense of it from the average point of view, it'll be a lie.
Right.
The average you get is a lie, because it's actually the noise in the system that's the important feature of the system.
Yeah.
I
am wondering how long
and really
how long
it's the
should we
secret
stall?
of probably a few more minutes,
Okay.
because it is Friday morning, but we can wait for
It's good. It'll be fine if we have a small group, because this is like it's like a collective exercise, so we actually need input from people.
Yeah.
And yeah, it's going to be interactive. Yeah. We had a leak in our department, in our new building. It caused a lot of damage, and they're still repairing that. They're just replacing the carpet that had been damaged and moving people back into their offices. Thank you. Yeah.
Wow. Yeah, I heard about it. And it's not the first time. I guess I've seen out the first accident like last year.
Yeah, no, when we first moved in, it's
Yeah.
actually, the problem is that there was a problem with the design. Yeah, no, you're good, Ku. We're stalling just a few minutes to let people join, so you're not behind yet. And in fact, you're not going. This will be a pretty slow progress kind of activity. But yeah, we were talking about the flooding in my office building. So we have a brand new building, and apparently it's a LEED building, so it's got all kinds of environmentally friendly features. And I don't know if this is related exactly, but the air conditioning system has some kind of a big basin that sits on the roof, near the roof, that catches water condensation from the air conditioning system and recycles it back. And apparently when they put that, there's a big tray that collects all the water, and they didn't level it properly. And so when it gets really hot and it gets really humid here, and there's collecting lots of water, it can overflow and then run into the ceilings and into the offices. And we lost a computer or two, and some papers, and lots of rugs, and yeah, it was kind of a mess.
Oh God.
And that's happened twice now. The first time they didn't realize what was going on fully, and the second time now they say that they've they've definitely fixed the problem. So hope, well, fingers crossed. But
yeah, until the next leak of something else, right? So
it's very appropriate because we're going to do a lot of debugging today. I expect many times today in our session that we'll have some errors that confuse us, and we'll have to track them down. So we should be humble about our abilities to get things right the first time. But it's bad when it's a building, right? So what we're going to do today is build a model. Thought the best way to get people comfortable with building models in BioNetGen and using the kind of rule-based multi-site features is to do that for a non-trivial example and to work through it. And really, my goal is to sort of work through the thought process that leads to encoding it. And one of the things that we're going to see is that, I don't know that we'll try many different approaches, but there are always many different approaches to coding models, to taking the biochemistry and then formulating a rule-based model describing that. And there are trade-offs that are involved in those choices. And we'll need to come to terms with some of those things as we go along. And what I found is that oftentimes it takes people a while to see the different approaches that are possible, and you really have to think. It's like learning any new programming language. The virtue of learning a new programming language, beyond all the cool library functions that you can get access to, is really learning new ways of thinking about problems. And the rule-based way of thinking is really a different way of thinking than the sort of standard way that we normally encode reaction networks. And so it takes some time and training to really think about it and to take full advantage of the approach. And even people who have been doing it for some time often don't necessarily know all the possible tricks that you can play. And it's like any of these. I remember when I first learned, when I first started graduate school, I learned Mathematica, which was kind of a relatively new thing at the time. And Mathematica is a language where you can often do things very efficiently, but you have to think very carefully about how you do it before you write the code, as opposed to writing Fortran code. You just the standard model was just you just crank it out, right? You don't think very carefully about what you're doing. And there are definitely pros and cons of that strategy. So, all right. So without all of that as introduction, what we're going to do is I pulled up a paper. Oh, I have to share. I'll share my screen. And so Tom mentioned a paper that he had been involved with a number of years ago and showed a scheme from it. And I thought, I should just take one of these standard kinetic schemes from one of these Synapse papers, because there are a lot of different in computational neuroscience, as many of you know, there are a lot of sort of classic models that are fundamentally involve a multivalent binding process, and you often see diagrams that look kind of like the one that's shown here. This is a pretty decently complicated state diagram of calcium sensor in a particular, this one is in a particular kind of neuron that Tom can tell you a lot more about than I know. But the key idea is that you have at the fundamental level, at the sort of single unit sensor level, you have multivalent binding, multiple calciums combined to two different proteins that form a complex, and they're coupled in some fairly intricate way to the vesicle release machinery that's present at this synapse, at the presynaptic junction here, and that the sensors actually illustrated in this picture. Maybe Tom, you can describe in more detail what's shown here, and then we can go into the kinetic scheme.
Okay, sure. So first show maybe the title slide of
Oh
the
yeah,
paper.
sure, sure.
That was just barely cut off. Okay, so this is PLOS Comp Bio 2010 with Sahita Nadkarni as first author, me, Terry, and Herb Levine. Okay, so now you can scroll down to the picture. So what you're seeing here in this picture is in panel A on the left side, a presynaptic axon shown in blue, and a little segment of it that's like half micron by half micron by 4 microns long. And then the little green cube below it is kind of the very canonical picture of the head, spine head of a dendritic spine. And this is in an area of the brain called CA1 area of the hippocampus. And what we're modeling here is rat hippocampal area CA1 synapses between that axon and the spine head. The axon is a Schaefer collateral axon that comes from area CA3. And then on the right-hand side of panel A is a zoom shot of the active zone area, the pre and postsynaptic active zone area. And the model that was demonstrated here in this paper was of the presynaptic release machinery, the calcium dependence of that presynaptic release machinery. And the little white spheres represent docked synaptic vesicles. And on average, in this type of synapse, in area CA1, on average, there are about 7 docked vesicles. So there are 7 of them there. Some of them are hidden behind. And the little red glyphs below are just very cartoonish representations of the calcium sensor, which binds, and the kinetic diagram of the behavior of the calcium sensor associated with each vesicle is shown in panel B below. And but what goes on in this model is when a action potential arrives on the axon, it depolarizes the membrane, and voltage-dependent calcium channels, which are shown in the little cluster there, and they're not necessarily clustered for real in actuality. Most likely, they're distributed at random around the synapse, with a few of them being inside where the docked vesicles are, but most of them being randomly distributed around the synapse. This is a controversial arrangement, but there's getting to be more evidence of that. And later this year, we've been collaborating with Christian Rosenmund and Marissa Brockman on making a more sophisticated, updated version of this model for a paper that they're going to publish, and I'll be part of it. It's a further development of the model that you see here in panel A. But when the membrane depolarizes, the action potential causes the voltage-dependent calcium channels to open and let in an influx of calcium. That calcium diffuses throughout the active zone and can bind to the calcium sensor. And there, within the cytoplasm of the axon, there are calbindin molecules that act like a buffer of the calcium. And then there are PMCA pumps in the membrane that are responsible for creating a calcium homeostasis and bringing everything back down to the resting level of calcium. Resting level of calcium is about 100 nanomolar. So it's a very, very low concentration. And literally, the number of calcium ions that you see shown here, free calcium ions, the little yellow stars here, literally, this is not an exaggerated view of the count of the number of free calcium ions that there might be in a little slice like this. There might only be 3, 4, half a dozen free calcium ions in the vicinity of the docked vesicles at rest. So it's a very, very low calcium concentration. And then in B shows the state diagram of how calcium binds and activates the receptor. Activates the snare complex so that it can cause release of a docked vesicle. And Jim, I don't know if you want me to describe.
Well, I can
Yeah.
I can sort of walk through this. So the sensor is thought to be comprised of two different subunits, which are not named here, but we'll name them in our model. It's site 2 and 7, right?
Yeah, site.
SYT.
Yeah, which stands for synaptotagmin.
Synaptotagmin, right. And so what's shown here is the kinetic scheme, and there are two proteins that contribute to this sensing that can lead to vesicle release, and there are two forms of this release. Well, actually, there are three, but two activated forms. One involving the so-called asynchronous mechanism, and the names for the nomenclature for that is a little bit strange, and maybe Tom can fill us in a sec. But they're basically one of the subunits. They call it S here, is responsible for the synchronous release, and which is one mechanism for vesicle release, and the second one, the asynchronous sensor, is responsible for the asynchronous release. And the assumption of this model is that in order for one of the two sensors in the sensor complex, in the sensor pair, to trigger release, all of its calcium binding sites have to be bound. So which in this way that the scheme works is that, so if we look at if we just start out here in the upper low, what do we call this?
The back left corner,
The
lower
lower
left back.
Yeah, I'm really terrible with that. Okay, so we start over in this corner here with A0, which means no calcium's bound to the asynchronous sensor, which happens to be site 7.
Yes, SYT7.
SYT7. Then if we bind two calciums, so we take each jump down into the left here to get to A2, that represents two bound calciums to the to site 7, then that state can undergo so-called asynchronous release, which occurs at this rate A gamma. That's what this diagram is showing us, as opposed to the synchronous release rate, which is at gamma. And so so you only have to have two calcium binding events happen to get asynchronous release. Conversely, in order to get synchronous release, you have to bind 5 calcium molecules to the synchronous sensor, which is known as SYT2.
And shown as S in the state diagram here.
Yes, shown as S here. And then there's one state in which both are fully bound. They can undergo both forms of release. There's about I think a 40-fold difference between the release rates. I think this A is like 0.025.
Yes, that's right.
And then there's also a process of spontaneous release that can happen, but that's several orders of magnitude slower. It really doesn't contribute. And in fact, in all the simulations that we've run, I haven't seen a spontaneous release event, I don't think. So it's very low in frequency. I'm not really sure. Maybe Tom has a thought about why spontaneous release can occur from all of these states.
Well, so I think the way the release mechanism is understood to occur is that the synaptotagmins hold and dock the vesicle in place and keep the vesicle from touching the plasma membrane and keep it apart. But thermal fluctuations can bring the vesicle closer or farther away from the membrane, and every once in a while it can touch the membrane, and when it does, there's a fusion event between the membranes, and which would really like to fuse together and come together, but there's an energy barrier to get over before that can happen. But thermal fluctuations once in a while will allow it to happen.
Yeah.
And so, yeah, but it's so rare. I don't know why it's even included in anyone's thinking about the synapse, but yeah.
Yeah, what we'll see is that so the calcium concentration is never zero. So there's never zero probability that one of the sensors can be bound. So there will always be some low frequency of release events that take place, even at the background calcium concentration. And it turns out that is it the ones that occur at background are the asynchronous events?
Yeah.
Yes, and you only get synchronous release when you have higher calcium concentrations.
Right.
Transient ones.
Right.
But
and maybe therein lies the conundrum about this.
Yeah, it's actually quite an interesting, rich model. But from our point of view, we're going to focus for a bit just on how do we encode this kinetic scheme. So, I mean, one way you can do it, you could just write a reaction network that has all of the species, so S0, A0 up to S5, A2, and so I should mention what's the difference between the upper and lower. So in this model, what they have a process. So once the states on the bottom all have a vesicle, all have the capability to release, to induce a vesicle release event. And there's in this model that they published, they added an additional state. So once vesicle release happens from one of these edge states, the complex, the sensor goes into the so-called refractory state that's denoted by the star that you can see, in which it's unable to induce another release event. And then there's some rate of relaxation from the starred states back down to the vesicle releasing states. And actually for our purposes, we're actually going to include effectively this a refractory-like state that's not exactly the one that they were modeling in this paper, but it's practical because what happens is that once the sensor induces the release of its associated vesicle, there's some time before a new vesicle appears that it can induce the release of again. So even if it remains in an active state, as soon as a release event happens, then it's going to go to a state where it can no longer release for some period of time until a new vesicle comes along. And we can model that also as a first order process with some rate. And so that's what we do. So in order to make a reasonable model of vesicle release, we actually do need this full state picture, which involves at least 30 species. And each of these species can undergo 3 or 4 reactions. So this whole kinetic scheme to write down by brute force is it's a non-trivial undertaking. You could probably improve the write some for loops to improve the efficiency of that and develop your own indexing scheme and whatnot. But the rule-based modeling framework makes it very easy to do that without having to write a lot of certainly like low-level code, and also makes it possible to represent this in a fairly standardized way that most other, I think, users could understand what's going on pretty well. So that's what we're going to try to do today, and I think it's a nice example of how to apply BioNetGen type modeling in a non-trivial example. And you'll see we have to make some choices along the way. So I think we'll leave it there. We're gonna have to grapple with some of the particulars of this scheme as we go along, but I think it makes sense to do that as we start to try to write the rules. So the first thing that we'll do is we're going to use our VS Code implementation, and I've already walked through. Tom and I worked through this exercise yesterday, so we have all the code. But I'm gonna start again. Sorry, just closing my music there, and we'll start fresh with a new window and make a new project. So we can, let's see, I want to make a new, so I would encourage everyone, to do basically what we did with Adam yesterday, and gosh, there we go, and make my brain is going to work again soon. Okay, I just made a random folder, and then in let's just make we'll call it the what have I been calling this, snare? Is that a good name for it, Tom?
Sure.
Okay. And so now we have a new project folder. I had been thinking I was going to make a repo. Oh, there are questions in the chat too. Well, do let me know if there's the paper, the link to the paper, I can post it in the chat. It's also, I put it very efficiently on the Google Doc as well. This is the paper here, yeah. Did that get answered already? Did someone post the link already?
Yes.
Yeah.
Okay, great. Yeah. Yeah, let me know if there's anything else. Okay, so I feel like I should make this a Git, but we can do that. We can create the repo later on. We're not going to need it for the time being. So let's just call this snare1.bmgl, and we can get our nice model template. And so we need to figure out an approach to encoding, encoding this scheme. So we can, let's just kick that can down the road just a little bit, and we can focus on the parameters that we're going to need for the model. So one of the nice things about this particular model is it doesn't have a large number of kinetic parameters, even though the scheme, as you see, we said what, more than 30 states and well over 100 different reaction rate processes. There are only a total of basically 4 fundamental rate parameters, and then another 5 parameters, one of which is this epsilon, which we're not going to use. So there's a total of like 8 basic rate parameters for the model. We also need to know something about the calcium concentration. So we can start out by just incorporating these rate constants, into the model. Hide this for now. You might have to cheat later on, but we'll try to do this from scratch now. And so we can start we'll just put in the rate constants for synchronous. So these are rate constants for calcium association with the synchronous and asynchronous sensors. Should be Ks plus, Ks minus, Ka plus, Ka minus, B, gamma, delta, epsilon, A. So we can start with it's Ks plus, and let's see if this works. Put it in the wrong place right off the bat. And this is 0.8. normally I would want to put some nice comments in here, but since we're doing this live, let's just I'll forego the comments about. Usually, a good practice would be to put, like a comment here that says this is in molar per second, and so on and so forth. 3.82 E6 K minus Ka minus. And one thing to keep in mind, you can't use the plus and minus symbols in BioNetGen strings. You'll get an error. That's why. So instead of, if we have a plus or minus, which is a common thing that you'll see in rate constants, we use P and M to denote plus and minus. Usually, it's just a standard convention that we follow usually. And okay, and then there's some additional parameters. And again, it's a good idea to put comments in here to keep in mind all the different things that are going on. Gamma, so gamma is the synchronous release rate. That is 2E3. Delta.
Simple question, but how did you get it to show the dots for the spaces?
That is a feature of the editor and I think it's under view render white space. Is that? Yeah.
Yep, that's it. Thank you.
Yeah, that's super useful.
Yeah, sometimes it's a good idea to turn on word wrap too, especially like when I have the screen zoomed in so you guys can see it better. We'll get wrapped lines. Right. Delta. I'm trying to remember what. Oh, E-3. Don't forget that.
Yeah, don't forget that.
Where does delta come in?
Delta is the spontaneous.
No, it's not. The A is the spontaneous. It's a fact.
No.
A is the so
no,
the spontaneous.
Delta is the spontaneous release rate.
Oh yeah. Yes. Yeah. I'm gonna put a comment in here so I remember. I always forget because I didn't have it in the. It doesn't matter.
Yeah.
So this is the A is the modifier for the asynchronous release rate. Okay, so this wasn't too bad, and mercifully it turns out that as far as we can tell anyway, these parameters are correct. For those of you who have done a lot of modeling, you know that usually when you try to reproduce someone's model, there's at least one parameter there's at least one typo in a table of this sort. There's probably typos other places we didn't find, but here we're okay. So okay.
So you can see that that delta spontaneous release rate is about 1 an hour or something, or a little bit more than 1 an hour. So it's pretty slow.
Yeah, we're going to be doing simulations of less than like a fractions of a second. So yeah, that's okay. So now we actually have to deal with some fundamental questions, which is how are we going to represent this sensor? And there are different strategies that we could adopt. I wish I had an easy way to. I didn't bring my iPad in today, actually. This mouse makes me a little bit crazy because it's very it's sensitive. It's got it's like a touchpad on the top, but it really likes to just. I think it's like a combination of when it gets slightly nervous and my hands sweat just ever so much. It just makes it really sensitive. Okay, all right. We don't need to talk about this. Let me I'm just trying to think of the best way to show. So, we need a way to represent this complex. So there are a couple of different ways we could do that in BioNetGen. One of them would be something like we could make one snare and we could have synchronous, we could have the synchronous sites that we could call, say, S for synchronous, and there would be like 5 of them. And then we could put in asynchronous sites. There would be 2 of those. And so one virtue of this, so each of these would be a binding site for calcium, and they're identical. And so one virtue of that is that in any rule, BioNetGen is going to treat them equivalently. So it would be very convenient to represent binding in this way, and we could write rules, you'll notice that the binding to the synchronous sensor and asynchronous sensor, if you look at this scheme, they don't affect each other. They're independent. So we don't have to, in the rules that consider binding to one or the other, we don't have to mention the one that's not involved. But so this is a possible strategy, and then we could represent calcium as just having a binding site, and it's going to bind to this snare complex either at the S sites or the A sites. So this would be a very explicit way to represent what's going on: calcium binding and the snare complex. And that's actually that's the strategy that I started out thinking to do, until I realized something about this scheme, which makes that a little bit more complicated than I wanted it to be. And that is these, and maybe now it would be good to zoom in here. If we look carefully at the binding, along one of these, so the S binding, the binding of calcium to S along one of these lines. So this represents, if we just started S0, A0, so the binding of the first calcium to the synchronous sensor goes at a rate constant 5 Ks. And that I understand and can be rationalized because there are 5 binding sites for calcium, and this Ks plus rate constant represents the binding rate for a single site. So because there are 5 choices, the rate occurs at 5 times the single site binding rate. So, and then when there is 1 site bound, then there are 4 open sites. So the rate is 4 Ks and 3 Ks to 1. Okay, so that I understand well. And actually, in this sort of a framework, BioNetGen would handle that gracefully. It would, if I made a rule, so if I make a reaction rule, snare S plus calcium B binding to form a bond between these two, like so. So this is an explicit binding model where I'm explicitly representing the binding sites and the binding sites and the bonds. So this rule would generate the all of these spontaneous, all of these synchronous states, and the rate of each of the reactions that it would generate would all take into account the multiplicity of the binding sites naturally. So it would be very nice. And actually, why don't we just see that as just a demonstration? We have some time this morning, so we can have a look at that. Oh, I put that in the wrong place, didn't I? Okay, so let's just see what would happen. And so I actually have to declare my species also. So
has to be in your begin.
I keep doing that today.
Yeah. Need space.
The syntax highlighting is very helpful for that, because nothing is going to work nicely until it's complete. So, or look nice until it's complete. So just to see we want to verify that BioNetGen would do this correctly. So, and I'm modeling for you a strategy that I would encourage people to take, which is, don't like, we could write out this whole scheme. We could say, okay, we're going to do it this way, and then write out the whole scheme and generate, this very complex network all at once. And undoubtedly we would make a ton of mistakes and have to debug them. And some of the mistakes would be quite hard to find. So I always encourage people to take a step-by-step approach, break it down, and make sure that you understand what's going on at each step of the way. Then it's more time consuming on the forward end, but you're going to spend a lot less time debugging. So, okay, so let's just see if this works, having said that. Yeah, and it did. And okay, so we see that we now, actually, we can see the process of network generation. So the log, we read in our 8 parameters, 2 molecule types, 2 species, and 1 rule. And that 1 rule generated, boom, 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 7 species and 5 reactions. And that's all it did, because that's all we asked BioNetGen to do, is to generate the network. And let's just have a quick look at, I don't think we looked at the net file before, but we can see what this rule did now. So we started with our snare complex with its 5 identical S sites and a calcium. And those were the 2 initial species. And the first thing that can happen is that 1 calcium binds, then 2 calciums can bind, then 3, then 4, then 5. Okay, and so we are up to 7 species, and we see that if we look at the reactions, so each reaction line here has an index that just denotes the index of the reaction. Then these are the first 2. The first entry is comma separated list of the reactants. So these indices here refer to the indices of the species. So this reaction is 1 plus 2. So free snare plus free calcium gives 3, 1 calcium bound to snare. And we see that the rate, BioNetGen automatically determined that the rate was 5 times KSP. So that's beautiful. That's exactly what we want. And we see that then if we follow these down, then the this is 2 is always the calcium species, and then but the 3 index 3 species index 3 is 1 calcium bound. So calcium binding to the 1 calcium bound state has a multiplicity of 4, and so on and so forth down the chain. And hopefully, is that clear for everyone? What we did here?
Jim, to me, it's not. I mean, if you can explain again the what you were saying, I mean, about the Begin reactions and how to kind of read and understand why the 5 times KS is, which one is which, the 1, 2, 3 that you see at the beginning.
Yeah. So the key here, the first number is an index of the reaction. Okay, and then the next set of numbers, the 1, 2, that's a comma separated list. Those are the reactants. The next set is our products, and then the rate constant, basically. So here we have the first reaction. We have 1 plus 2 goes to 3. So we can actually, BioNetGen can output a more verbose format that shows you the names of the species, but you're going to get, they're fairly long. And like by the time you get to 7, you get this whole thing, right? Which is pretty long and complicated. And another reason for doing this step by step and looking at like just what the action of a single rule is that, we can understand what species 7 is here pretty easily. If this were in a much larger list where there were 50 species, trying to sort through all of this gets very cumbersome. But right, so this is a fairly simple place to start. So we have 1 plus 2, so snare plus calcium, and then it forms species 3. That's this complex calcium snare here. Okay, and then the last thing is the rate constant, and we see that it gets the rate constant that we declared for the reaction in the reaction rule, but it also generates this multiplicity factor 5, because there are 5 ways that calcium can bind to the free snare complex at the synchronous site. Is it clear?
Yeah, thank you. Yeah, super clear now.
So I highly recommend doing this sort of thing especially when you're trying out a new scheme, or not 100% certain about what's going to happen. So just to continue this, and what we can do, we can show that very easily. Then we can get the asynchronous rule also. So now we just change this to KAP. And this will now quickly generate, these two rules will generate the whole set of species of one level here. We haven't included yet the vesicle association state, but we'll get everything else. Okay.
Sorry, Jim, I'm a little confused about the other file that you were showing. That was just for validation, or I mean, why is this is like you have all these rule-based mechanisms and you don't seem to take any advantage of it. Is that?
No, so okay. So this is the model that we're developing, right? The BNGL file. And what I'm showing you is the result. So yeah, I should go back here for a sec. So this generate network command, what is it doing? It's taking the rules that we defined and it's applying them to the species that we started with, the so-called seed species that we just shortened to call species. Okay. And it's doing that iteratively until it can't find any more reactions to generate. So the first thing it does is it says, okay, I've got snare, I've got calcium. I have a rule that binds snare to calcium at S, and I've got another one that binds it at A. And so right away in the first round, I can make two different reactions, one for binding to S and one for binding to A. And so for the first round of network generation, actually, we generate two new reactions, one for each rule, and two new species for the one for each site that we bound to. And what I'm showing you here is something, the net file is not something that we normally would just look at, right? It's what where BioNetGen stores the reaction network that's converted to equations or Gillespie simulation or SBML or MATLAB code or whatever we're going to use to do the simulation. But we don't normally have to look at it, but it's useful for debugging.
Yeah, I think I was just confused because I was thinking about it in the ChemK2 context, but of course you can't.
Yeah, okay, at some point it runs out of,
yeah,
we can't even do it.
Yeah.
But even in a model like that, it's not a bad idea to start with something that's simple and where we know it's not going to explode.
Right.
Make sure that it's doing the things that we expect it to be doing. And you know, and admittedly, there's definitely some. We can definitely develop better debugging tools for some of these. For you know, within this framework, that would let you graphically inspect species and so forth. I mean, RuleBender provided some of those capabilities, but I think one of the things is you have to train people to use those. It's like, and not that many people, learn to do it that way. So, so that's why one of the reasons I thought it's fun to go into this and show it a bit. So this just shows, so we have the two rules now generated 19 species and 27 reactions. I feel like it's, 19 species and 27 reactions. And you can see what they all are because of this, and I'm trying to remember, is that, I feel like, there's 15 plus 2. That's where the 7, no, but wait a minute. Can I not count? It's 3 times 6. Yeah, that's 18 plus 1 for the calcium. That's where the numbers come from. So there are 19 species. We can go and verify, the most fully bound, fully complex species has 7 calciums. And we can see that the index here is the index of the bond. So this calcium here that's got 1 is bound to the snare at this A site. And 2 goes to 2, 3 goes to 3, et cetera, et cetera. So like the 7th calcium is bound to this 7th S site. And so all is in good order. And we can see that the, if we look, so these are generated in the order of the network generation rounds. So the first reaction is the binding of calcium to the uncomplexed sensor at the S site. So there are 5 of those. So we get a multiplicity of 5. And the second one is the binding to the asynchronous site. And there are 2 of those. So we get a multiplicity of 2. So now, before we saw 5, 4, 3, okay, 5, 4, 3. And we can see that for the asynchronous sites, we have 2. This is the first one binding. And then the second one is down here. It's actually BioNetGen is this, this comment is showing you the rule, the index of basically the index of the rule that generated this reaction. So this was an R2, and R2 was the binding to the asynchronous site. Hold on, let's see, 2, 3, 6 has a multiplicity of 2 also. Oh yeah, that one, that is, so 3, this actually came from the second round of network generation. So yeah, state 3 is the one that already has 1 calcium bound to the synchronous site, and then binding to the asynchronous site also has that multiplicity of 2. So I'm fairly confident that if we go through this list, we'll find out that all the multiplicities are correct. We can spot check one more just for sanity's purpose. So this one has a multiplicity. This is an asynchronous binding 2 to 14 with a multiplicity of 2. And I'm going to guess that the state 14 is one in which all the synchronous sites are bound. And so there are 5, and yes, state 14, they're all 5 bound. And then,
sorry, may I ask?
Yes, please.
So what's the 0, the last entry there on the line that you're on?
Oh, this is the number. This is the initial number of these.
Oh, so that's why it's 1 on those first 2.
Yeah. So these were the ones that were initially present. And then all of these are species that can occur in the system, but that are not initially present because we didn't declare everything that wasn't initially declared is got a concentration of 0.
Right. Okay. Thank you.
Yeah.
Jim, another question. Sorry if this is a basic knowledge gap. If we cared about which one of the S sites is bound, so if it's the site,
yeah,
do we have to label all of them different things, like different sites?
Yes. So if they're distinguishable, so if there's an S1 and an S2 that behave differently, maybe the affinity is different. Just because maybe the protein, the amino, there's a motif, but there's a slight difference, or so that causes the affinity to be different for those sites, then yes, you would name them differently. I mean, the cost of that would be you'd have to write, additional rules, right? So, here BioNetGen is being very literal. Every S site every site that's named the same gets treated exactly the same. There are subtle ways you could modify that behavior, but I think that's a good. And so I would say that, it's not something that we do very often, but you can bind. You could break up the degeneracy of these sites by binding them by having them bound in some way, by having a graph that represents their connectivity. But I wouldn't recommend that. It's going to be very complicated. But so yes, if you wanted to make distinguish between the sites, you'd have to do something like this, and then you'd have to write rules specific to each one of them. And that could be an appropriate thing to do, but in this model they haven't made that distinction, so we're sticking to this approach. The interesting thing is, this is almost like this whole example of a way of doing it is this the kind of the most literal way, representing each site as a separate object. Ultimately, we're not gonna go this route for reasons that I think we'll try to make clear soon. Right. So far we generated this whole all of the species on one of these levels. It's actually the lower level. And we could account for the multiplicities going across the rows and also going across the columns. We can, if we make these rules, if we make these reactions reversible, then we can get the unbindings as well. Ks minus K minus, and this now adding those reverse rates will not add any new species to our system, but it'll add all the reverse reactions. So we should have approximately double the number of reactions. And now we have 19 species and 54 reactions because all of them are now reversible. And we can look at those reverse reactions that are generated. They're helpfully labeled here. And what if we now look at the scheme, so we can see that the reverse reactions have multiplicities associated with them as well in the opposite order, 5, 4, 3, 2, 1 for the synchronous site, because in the fully bound state, there are 5 different calciums that can dissociate, and then 4, and then 3, and then 2, and then 1. So let's look for the reaction, the dissociation reactions of this species 19, in which all the calcium sites are bound. So the dissociation from both the asynchronous and synchronous sites should have their max multiplicities of either 2 or 5. So let's look for species 19 in our list. We have, in fact, we have 2 reactions that involve dissociation of species 19, and both of them have the multiplicities we expect, 5 for the synchronous site and 2 for the asynchronous site. So that's good. So we matched, this is the state that we're talking about, and the dissociation has a multiplicity of 5 and a multiplicity of 2. So,
sorry, can I just interrupt with a basic question probably? How did you get the snare /1 net file opened? When you run a thing?
Yeah. Okay.
Yeah, I've actually had a mistake in it, so I had to go over, I missed like 2 letters and I had wondering why I had less reactions. So I got kind of,
Okay.
But now I realized, yeah, I don't have that open.
So when you're in your model in the BNGL file and you hit run, then if it runs properly, and so if it runs without an error here, then it will make a new directory. I can just do it and show. It makes a new directory.
So for me it ran properly, but it's never made a new directory.
It should make a new directory.
Right. Okay. I will.
Which you then should be able to navigate to, and the net file will be there.
Yeah. Okay. I will have a look at a start, like later on, whatever I've done. I don't know what could have happened.
One thing I encountered, I didn't generate a network. It was because I didn't have the begin species section.
Yeah, there's a little bit of an issue that in the terminal, sometimes it doesn't refresh and show you the bottom of the line, so you don't see that you don't see the error. It updates it very slowly sometimes, so that's something that we'll try to iron out. But generally, if you don't see something pop up here, then you should scroll down and check out the log from the terminal window. It should give you an indication as to what is going on.
Right. Yeah.
If it runs correctly, you should see finish processing file, and it will generate this whole thing. Oh yeah, this is the file, the BNGL. It should have written a file to this net file.
Yeah, I've got that, but nothing is happening. But I will have a look. Thank you so much, though. Yeah, it might be just something.
And no one should worry. I mean, this is the pace that I had thought we would go at. So, I don't know exactly how long it will take to get through everything, and we may not get through everything. But this is really meant to be an interactive learning session. So please, ask questions. And if you're confused, something doesn't make sense, please shout it out, because that's why we're doing this. And I think, yeah, hopefully it's helpful to everyone. So yeah, this net file, it should appear in the timestamp directory. And that's the only thing that will appear. We're not doing any simulations. And then we can look in it and see what's been generated. And like I said, doing this kind of spot checking, especially at the early phases of working out a scheme for representing the model biochemistry, I think is really useful. So,
Jim, just one more question. I mean, this is very useful about the reversal reactions. I mean, you mentioned the multiplicity is what we expect, and what about the B that is also changing the exponent?
I was going to ask that as a question to the group. What's missing? So that's exactly what's missing, right? Yeah. So when I first did it, I started making this scheme, exactly this, because I knew I could encode all of these states very concise. I can generate all of this very easily with just these two rules, right? And I had to squint. I didn't notice the B's at first. And so what are those? What's going on there? Where are those coming from? Does anybody know?
Or we could ask, what do people think it means?
Yeah. What is it? Yeah. What phenomenon? But physical phenomenon, physical chemical phenomenon is it representing?
And notice it goes from B to the 0 power, B to the 1 power, B to the 2 power, 3, 4.
But it only affects the off rates.
Yes.
I'd be wrong, but would that be repol?
What did you say? Sorry, I didn't miss what.
Repolarization.
Repolarization.
I'm not big in neuro. Love it though.
It's not a neuro. It's not a neuro
No,
thing.
this is a basic enzyme.
Yeah, it's basic. It's basic enzyme kinetics. Yeah.
Sorry, I'm trying to get the software.
Don't
fixed.
apologize
like
at all.
paying
This
attention.
is like it's not obvious. In fact, what's funny about it, and not to give Tom a hard time or anything, but in the paper they don't mention it, and the B factor appears in this diagram and it appears in the table, but it is not mentioned at all. And I think the reason for that is that it's they built this from a previous model, which was published in Nature. That was
published by 2 other groups.
Yeah,
there was already a history for it, and rather than repeat all that history in our paper, we just referred to it.
It's all good. It's just
right. Otherwise, if you have to re-explain everything in every new paper, you get nowhere, right? So, yeah.
Not to be too critical. I completely understand. I think I would have loved to have seen one sentence in the text that referred to what this B parameter was, because like I didn't know. I missed it at first, and then I was like, when I looked at the table, I was like, what is this B? And then I squinted and I saw in the diagram, oh, there's B. Oh, I see what this is. And I think, yeah, probably most readers would, actually, I don't know if most readers would know what this is representing. They'd have to go back to the original model probably to see an explanation of it. But so any other guesses? There's a simple one-word answer to the question, what does this represent?
So we have some hypotheses about it. In the chat.
This is with enzyme kinematics, right?
Nonlinearity and calcium binding release okay, but is it just to do with the stoichiometry? It is not a stoichiometric effect. The stoichiometry is entirely incorporated in the stoichiometry labels of the complexes here. So the rates are the stoichiometry is does determine this multiplicity factor that like 3 in this particular reaction that I'm pointing to. But the B factor is not a stoichiometric effect. Not directly, no. Yeah.
There's a
So, Tom, I would argue that the fact that the audience is confused is a good reason why it should say something.
Yeah, absolutely, should have.
Yeah. So
B is not buffering.
B is not buffering. Yeah. So it's a cooperativity factor.
In fact, it should have been called C, right?
But I don't know. C could be many things.
No, C for cooperativity, right?
Right. No, I know. I know.
Yeah. But it's called B because that's what it was called in the original two papers that we're building on here.
So
and those papers weren't our papers; they're other people's papers, right?
So what? It's a little bit subtle. I mean, to me, this is obvious, but that's because I think about this stuff a lot. But what's happening is that the forward rate's not being modified, but the reverse rate is being modified by this B factor, which is a function of the number of other bound calciums here. So that's why I hesitated when someone put in the chat stoichiometry. It is a function of the stoichiometry, because so what's happening is that the dissociation rate is being modified because of the presence of multiple calciums on the same binding to the same sensor molecule. And the extent of this effect is proportional to the number of calcium-calcium interactions on the sensor. So when you've got 5, there are 4 other calciums there's the calcium that's dissociating, but there's also interactions with 4 other calciums that are bound on that protein that contribute to this cooperativity. And so that's where the 4, basically it's a multiplicative factor here, B to the 4.
I see it now.
Yeah. The reason that it's multiplicative is that at the end of the day, it's due to a free energy change, and the free energy affects the rate as exponentially. So additivity in the free energy difference, and here there's one. Basically, you have 4 interactions, so there's 4 times a free energy difference, gives rise to an exponential factor on the rate constant. I'm going to leave that aside for now and just take that as a given, because I don't want to get too into that, and since it's thermodynamics, it's confusing sort of inherently. But this is a fine formulation of the model, and something that we need our rules to take into account explicitly. So this scheme, so the way the scheme that BioNetGen is generating is assuming that there's no cooperativity in the binding. Not only so that there's no cooperativity along any of these rows or columns, but the model, the actual model says, yes, there is this cooperativity factor, and what's more, it's a factor of 4. So the dissociation rate is decreasing by a factor of 4 for each calcium that's bound, meaning that the affinity is increasing by a factor of 4 for each calcium that's bound. So the more calcium that's bound, the higher the affinity. And so there's a strong cooperativity that favors the more fully bound states.
And so that's called negative cooperativity.
No, that's positive cooperativity.
Positive cooperativity, but it's positive.
It's negative free energy. It's
And I was getting it confused because oftentimes cooperativity appears on the binding rate, not on the unbinding rate.
Right.
Yeah. So we're decreasing the unbinding rate, which increases the affinity, and therefore it's positive cooperativity.
Right. So it's quite a subtle. It's quite a lot of ideas that are crammed into one little factor, which is a bit subtle.
Yeah.
And then that raises the question.
But sorry, Tim, just one question about that. So the fact that the 5 for the number that you're multiplying is changing, that alone means cooperativity, or also the, I mean, or more cooperativities with the b to the exponent. What we have already
set b to 1.
No.
If we set b to 1.
So I think what Lupe is referring to is the first coefficient there. That
I know. I'm going to.
Yeah.
5, 4, 3, 2, 1.
The condition.
Yeah. So
the second half of it is going to explain the answer I'm trying to get.
That is not cooperativity. That number is not cooperativity.
The numbers in front are not. Yes, are not cooperativity. Okay. That's simply counting.
Yeah.
So the model that we wrote here
is not
a completely non-cooperative model. There's no interaction between the sites whatsoever. There's no change in affinity for binding a calcium due to binding of other calcium in this system. So this is like the most generic, 7 site binding model with, 2 different types of sites that we could make.
With no cooperativity.
With no cooperativity.
Because the KSP and KSM, KAP, KAM are the same no matter what.
So if this were a different workshop, maybe next year, I would show you how to handle the cooperativity using a slightly extended form of BioNetGen that we call energy-based modeling, and we can use to represent cooperative interactions. But I'm not prepared to go into that today. So there is a simple way that we could extend this model to handle that cooperativity, basically by writing one more block that's called begin energy patterns here. Okay, and we add with one entry to this block, we could incorporate that B factor. And I haven't written it out here. I didn't do it this way. I will, after the workshop, I can post an example of this model using energy patterns that I think would be interesting. But for today, we're not going to get into that because I haven't given the relevant background for how that works. So this presents a little bit of a conundrum. How do we get that B factor? We're not going to have the rule has to get more complicated, right? And we can, BioNetGen actually lets you do this. Let me see if I can, I might try to do it off the cuff, but it's a little bit too tricky, I feel like, for something that we would, that I would encourage people who are learning this approach to do, because it involves something that we call local functions. But just for the heck of it, let's just do, oops, I'll just write it out and we can discuss briefly what's going on. Let's call it the number of sites, the number of synchronous sites that are bound. I'm going to make an observable that just counts up the number of S sites that are bound. Okay, and this observable will count up all the S sites that are bound in the whole system, the way that I'm writing it now. And we can do the same thing for asynchronous sites, like so. So we have 2 observables that that count the number of S sites and number of A sites that are bound. And what we need to do is make the dissociation rate a function of the number of synchronous sites that are bound for the synchronous binding, unbinding, and the asynchronous sites for the asynchronous binding. And in order to do that, we have to remember that we have to use an extension, a trick, basically a syntax that we haven't covered before that's called a tag. Is it ampersand or is it $? I'm trying to remember, because I don't do this very often. Is the highlighter going to know this, Sinan?
What is this? This is the
local functions for a tagging syntax.
I don't think highlighter knows about local functions right now.
Let me see if it should know this. Yeah.
Okay.
It's
I heard.
Hi, Kitty. It's the examples are there's examples of this that are given in the NFSim paper. Let me see if this works. It may not. Invalid. I have to.
As a side note, there's a new version of the shell that knows the reaction block. It didn't have the highlighting correctly a second ago in the net file.
Remember. I forgot that. Yeah, it's been a long time. I don't use local functions very often. No.
That's probably why I forgot to add it to the highlighter too.
It seems to be okay with that. It's like there's some subtleties. It's something I know how to. It's something I know how to look up, but and I didn't prepare to demonstrate this. I have to see if I can. Yeah. Okay. All right. I know what I have to find real quick. No, I don't have this. You think I have this? Miss it.
Local function.
Yeah. Even though I wrote the BioNetGen implementation of local functions, I forget these things from time to time. This is what I get for being too tricky. No, but what? I need the value. Oh, come on.
I found something on.
Yeah, it's the next. I messed up. It's the next chapter. You probably found it, Adam. I just have to.
23. I don't know whether that's it.
It's this. It's percent. Okay.
Oh, percents are recognized.
So the sole purpose. Sorry.
Percents are recognized.
Yeah, I thought so.
And I think I saw a double colon.
It will either is fine.
Okay.
it's going to unfortunately each one.
Jim, can you do me one favor really quick? Can you go to the extensions portion and
Oh, you want me to
reload it?
update? That's what you were trying to. I'm sorry.
Yes. No. Absolutely fine. I just want to make sure it's not updated. I know it's published.
It should. I don't know why.
Maybe it didn't propagate to max yet because I'm seeing it on one Windows. It's okay.
Sorry, it didn't propagate to max.
I think so because it's on. It's.
No, I just did. Reload required. Okay. All right. Yeah, I mean that's one of the things that's really nice about some of these IDEs, and VS Code is one of them. It very it's very robust in being restarted and coming back to the state that you left it. Okay, so we have our rule. Let's go to one of the ones towards the end, and we see that now this local function created a new entry here called __ reverse R1 local file. It's very unsatisfying, but we can see that all of these are exactly the factors that we.
Except it says b to the 1, and it should be b to the 0.
Correct. Yes, I forgot to.
It's got to be -1. Somewhere.
Yep. And while we're at it, let's fix the other one. This is NA.
Right.
So hopefully.
Well, then you gotta put your %.
Yeah, I have to tag it too.
Yeah, you gotta tag it.
And I apologize. This is a little bit of a digression in the sense that the way I originally did it was different from this, and I hadn't actually beforehand tried this out. I knew it would work, but I didn't try it. Okay, but maybe we could continue on in this actually and see if we can make the whole thing work this way. So now we've got. Oh, that's weird. That's wholly unsatisfying, but I guess we'll have to take it.
Yeah, 1 -1.
This local functions code was written with some very specific applications in mind, and it hasn't gotten the use that in some ways it deserves. But at the same time, I definitely think that using an energy formalism is better in this case. But this works. It does give us the right values. I think the simulation would run correctly. We can validate that.
Jim, please, could you share the current version of the file somewhere?
Yeah, you want? That's a great idea. Let me put the simulate command in first, and then we can. What are we going to do? That's about right. Just to make sure that it runs. Okay. I'm not sure that's. I'm not sure exactly what that is doing. What we would expect for those observables to look like, but. Right. Well, that's just calcium binding. Yeah, that makes sense. So what I should do is, how do I make this a public repo? Git initialize repository, pick a workspace.
Yeah, I don't think there's an easy way to make a public repo right away.
I think.
What is it?
Oh, but why? Oh, and now I have to.
to push it.
The link is covered up by the. Here we go, and I put this into chat. This is the power of the internet, man. Oh, wait a minute. That wasn't. Why did it give me that? Hang on. It cut off. Sorry about that.
Yeah, cut off.
That's the repo. And the file.
Thank you.
I'll post the link to the file for those of you who are not operating at the speed of Adam. Okay, so that's good. So yeah, so if I push changes to stuff that I modify, it will go right up. Will go right up there for everybody to see. Yeah. Okay. All right. So where are we? We got the scheme. Although at this point it's a little tricky. One of the tricky things about working with this model and these models of very complex systems is that we're building just like one little piece, but there's a whole bunch of other pieces, the voltage dependent calcium channels that open to allow influx of calcium, the calcium pumps, the calbindin binding and buffering, all of which have a spatial element. So we could build out all of these components in MCell, but each one takes time, and actually each one needs to be done correctly, needs to be validated. It's quite tricky to get all of this to work together. And so we don't even have validation tests for our basic calcium binding model at this point. But we will get to a point where we can compare to something that we know. And I'm just checking on time. So we started at 10:30. We're an hour and a half in. So I guess technically we have another half an hour to do this, right? So that helps to calibrate. I don't want to go too far over, and I know I'm gonna run out of energy and start speaking gibberish before too long. Especially since I had to figure out how to do the compartment, the local functions thing. Well, I'm glad we went into that, because at least I know it's probably confusing to people, this exact syntax, but at least we have something that works, and you've been exposed to it. And the other thing to note, I'll post in the chat just for reference, that this, I have way too many tabs, and then I have way too many Zoom things. The manual link where the local functions are described, and NFSim has a nice manual, is here. So that's worth checking out too. It'll explain a little bit in more detail how this all worked. But the key idea is that we created this observable that counts up the number of calciums bound to the synchronous sites and to calciums bound to the asynchronous sites. And then by passing an argument to this observable, which was this X, we restrict the scope on which it's evaluated just to the complex that we're in. That's the key idea. So here we tag this snare complex that is undergoing the reaction. And we want to know just the number of S sites that are bound within that snare complex. And by using this local function, we saved writing a different rule for each instance of the different numbers of S's that could be bound, right? Because the effect of multiple S's being bound is all down to its effect on this cooperativity factor. So we captured that cooperativity factor in a single term here. And like I said, the energy formalism lets you do that in a more, I think, in a more natural way. But at the end of the day, it's using local functions basically too.
Yeah, and this is pretty concise, I think.
It is actually very concise once you write it down, and it's a little bit tricky. Okay, so now what do we need to do? We want to have a model for the release of vesicles that occur. So when we're in one of these fully calcium bound states on the bottom leftmost row or the rightmost column, so that either of these, we want to have the possibility of a vesicle release reaction at the rates either A gamma or gamma. So we did not, when I set up this model, we didn't put in the vesicle, but so we need to add a VB.
Docked vesicle.
Oh, we called it DV, docked vesicle component. Oh, well, actually, yeah, we'll say this is 1. The default state will be to have a docked vesicle. You can get rid of the compartments block now for a second. And yeah, I'll say this. Susan asked a question about the hill keyword. All of that, all the keywords that we used to have for certain rate laws, had been superseded by the ability to make global functions. So that's what we definitely use global function syntax and don't use keywords, is what I would say. That's out of date. Yeah, and we're working on updating the documentation for functions. It's a long, sad tale about why that's not up to date at the moment, but we'll just, it's a work in progress. I know that this syntax is bad. Hang on a second.
And you got to fix your parentheses.
Yeah. Okay, so we're gonna explicitly model whether vesicles are docked, and then we're going to make the vesicle release reactions. The calcium binding is not going to have any be influenced at all by the vesicle docking. We're going to assume the scheme doesn't show it. It lets calcium bind and unbind to all of these states. So we don't have to worry about changing our rules for calcium binding. We're going to do the vesicle release rules. So the first one, we know that there's one, the S0, A0 state can undergo the spontaneous vesicle release. So let's just write the rule for that so we have it. So what we have to do for that one, strangely enough, is we have to write out the whole complex. So this one can, what did I call it?
I think you called it V release, capital V release somewhere. Or
I'm gonna cheat because my brain is getting tired. Yeah, we had something that looked like this. Yeah, these were the vesicle release. You see that I had a completely different way of encoding this in terms of indices that we've bypassed now. But for now, I just wanted to cheat by looking at this. Oh, I see why I never saw any vesicle release this way. There's an error here.
Right.
Yeah, I forgot that. So here, what's happening is we actually model explicitly the molecule involved, the sensor molecule involved here. But the one with the docked vesicle can go to one with a not docked vesicle, and then the vesicle has been released. Interestingly, about the way that I encoded this, I feel like this is what was meant. Maybe not, maybe Tom would argue. This release reaction says that the spontaneous release can happen no matter what the state of the calcium binding is.
That's
I think
correct.
that's what was meant to be there.
That's why it's called spontaneous.
Right. But the way it's indicated in this diagram, it only happens from this one state. So I'm not sure. I never saw a scheme, but I think this is what was meant.
Yeah, I think it's what it was meant too.
And it's not going to affect anything. So let's just go with that, because this reaction frankly makes me very nervous. That rule.
Yeah.
But so that we're gonna lose our docked vesicle, and we're gonna I think I called it V release, right?
Yeah, V release.
We should add V release to our molecule types, otherwise BioNetGen might get upset.
Right.
We don't have to add it to seed species because it will get generated magically, but
I think we said rate.
we do have to have a molecule type. And then this is the spontaneous release rate. So delta.
Delta, right.
Okay. So this is spontaneous. We can do synchronous. That's gonna be snare. And then what we have to have is that all the S's are bound, right? And I introduced this this wildcard. I don't know if anyone asked about it in the chat, but the plus here means that the site is bound. It doesn't care what the index is. It just means that there's something there. We don't care what it's bound to also. So this represents the complex that has 5 calciums bound to it. I could put all of them explicitly in. I could even go to my net file and copy out one of these where all of them are bound, but I'm not going to, but it's then this huge string, right? I don't need to deal with that. So yeah. So I can write this nice shorthand that means I don't have to write put the calciums in there. And then this thing can go to, and I need to reference it has to have a docked vesicle to release a vesicle. And then, oops, goes to undocked and then the rate for this should be gamma for synchronous release. And for asynchronous, I only need 2 sites to be bound because there's only 2 asynchronous sites. And it's A times gamma. That's the rate. And
that's pretty much slick as can be, I think.
Yeah. So let's make an observable to track the released vesicles. We're not doing anything with them. I just want to remember what I called them. V release. Okay. Very unimaginative. So this will track the number of released vesicles. And it's useful to make some additional observables that are our release site, that are the fully activated complexes. Here, when I used indices, so C, the C component represent the number of calcium bound. If there are the site 2 needs to have 5, that's the synchronous molecule. Site 7 has to have 2. And here we have to explicitly call these out. So we could call let's see. I don't know about you, but I find that let's just call it I find that the most challenging part of programming sometimes is figuring out what to call things. Actually, here, let's be really lazy. It's good to do things this way because it's good to check to make sure I didn't do anything wrong. So the sync act is going to track the number of activated snare complexes that have that are fully have all the synchronous sites bound, and async is going to do the same for the asynchronous sites. And it's only going to count the ones that have docked vesicles because those are the only ones that can release anyway. I guess you could go back and forth on whether you need that or not, but that seems like a reasonable thing to do. And I think that's all we need. We should be able to run this. That's cool. I haven't seen that before, the file history. It's because we added that mod. I didn't know about that module that we learned about yesterday from Adam. Okay, and we're running an ODE version of this. So lots of stuff is going on here.
Sorry.
Yeah.
Can you show the asynchronous rule again, just real quick, so I can?
Yeah, you know what, and I'll put that up. Yes, here you go.
Okay, thanks.
And I will also
push it.
Yeah. I should I guess I can just put all these.
And I think there's just one thing missing, but we'll get to that, I think, Jim.
Which is that?
So you release the vesicle.
Yeah.
But
oh, we did.
then...
Oh, yes. We forgot to do one thing, didn't we? So once the snare has lost the vesicle, it has to regain the vesicle. What did I call it? Vesicle docking. So that's a very simple one to do. We just have the undocked state goes back to a docked state. What we call this parameter?
I think we just call it kdoc, yeah.
So having created kdoc, we need to add that. You said that was 1?
1/5, or 0.2.
Yeah, that seems very slow.
Yeah, it is slow. But that's what it is in real life.
Yeah. Oh, we have preposterous values of the concentrations. That's something else that we didn't. Okay, so because this is actually in molar, because all of the association constants are in molar here. This is going to be the Achilles heel of our model, actually. The fact that we modeled the calcium explicitly is going to make it so I can't I can't easily do the things that some of the tricks that I wanted to do, but I have solutions for that, but I'm not sure we're going to get to how to exactly do all that. Oh yeah, you can do code folding too. That's pretty cool. I don't think we mentioned this before, but you can fold up blocks if it's convenient.
Oh, I love that. I love that.
You can have multiple blocks that have the same names. You could have a bunch of you could have a parameters block that's your standard unit conversion block, and you could stick that in and fold it up if you wanted. Okay, so yeah, so we haven't dealt with this concentration. So the actual calcium concentration is really tiny. What did we say? It's 1e minus
I'm going to let you complete your
7.
sentence.
The basal concentration is 0.1 micromolar, right?
Yeah.
And then the number of complexes, then we were typically doing in increments multiples of 7, because there are 7 complexes, there are 7 snares per active zone. So if we want to know the rate, so if we want to know the rate of vesicle release, if we want to determine that per active zone, we want to have an increment. We want to have a multiple of 7. So this would be like 10 active zones, and then we can see the number of releases per 10 active zones per X amount of time that we're going to simulate for. And we should have, I think this model is complete, and it should be comparable to the one that we had before for the basal calcium, with the exception that there's this, we have to be cautious because we've used, this is number units, but this is now explicit calcium concentration as opposed to number of molecules. So what we should do is, I think we made we can make another variable called CA0, and that should be 1e minus 7 times. Now, we essentially, there's a couple of different things we can do here. The thing that I'm going to do here, I'm going to try anyway, is just to fix this concentration by adding this $sign. So it's useful to do that here because our calcium is in different units than our snare complex number is. And if I don't clamp it, if I allow this reaction to happen, then the calcium is very quickly, that 1e minus 7 calcium is very quickly going to get depleted, because if it binds stoichiometrically to the snare, it's gonna go to 0 basically instantly. So I don't want to deal with the unit conversions here for other reasons, and I want to leave the units in molar, because I have all my rate constants in molar, and this is okay because we're just dealing with calcium.
So then can we say that the snares are 70 molar then when you release?
No, well, they're not. They're in their own units.
How can that be?
Yeah. How to explain that?
Because they're reacting with the plus sign.
But what I did by putting this $sign here is make this be fixed.
Okay.
So anywhere that calcium appears, its concentration is just clamped at 1e minus 7 molar.
Okay.
And so all that it's doing in this reaction that it's occurring in is its concentration is multiplying the rate constant, the forward association rate constant. And so
so that makes it like a pseudo first order.
It's making it everything pseudo first order.
Okay.
So we pulled some heavy duty tricks here.
So that's a trick, yeah.
It's a useful one, like I said, because otherwise I have to convert I mean, I could convert all the calciums to numbers. They're going to be very large, and I have to pick a volume for the system and all that. They're going to be large numbers, and I don't really care about the calcium. For sure, the sensors aren't going to deplete the calcium concentration at all, which is why I feel confident doing this.
Right, yeah.
Because the numbers are going to be, although it's interesting in your example, you know, when when you actually look at the basal level, the number of calciums per volume is pretty small, but they diffuse like crazy. So
yeah, they diffuse like crazy.
So
and also they're being buffered by the calbindin. So those stars are only the free calciums, right?
Right.
There's a lot of calcium there. It's just mostly bound to the
that's relevant. But the point is that the sensor is not going to be a significant source of calcium loss or buffering, right?
Right. Yeah. Right.
There's not enough of them.
Right.
So fixing
not compared to the calbindin and everything else, right?
Yeah. So one thing that I didn't do here too is I did this simulation only as ODE, not stochastically. And what I get is, what we're interested in is the vesicle release, and what happens is that there's a transient period where the calcium binding is equilibrating, and that's the number of calcium sites that are bound in the whole system. These are the asynchronous sites that are bound, and the synchronous and asynchronous. And we see that the asynchronous one equilibrates much more slowly. And the reason for that is that the off rate
KAM.
Yes, the asynchronous is slower. Yes. KAM is much slower, is 13 per second, which is, so that the half binding time is 1/13, or on the order of hundreds, at least tens of milliseconds, whereas the synchronous one equilibrates much faster, and we're seeing that in these time courses. So this is the synchronous and the asynchronous.
And that 13 per second is only for the first binding. The second binding is four times slower than that because of the cooperativity.
Yeah. So it's even slower. So the time to equilibrate is pretty long, actually. It's longer than our 200 milliseconds that we.
Yeah, maybe 500 or so, I think.
Yeah. Let's just run it stochastically and see if we can glean anything out of that. Nothing happened at all. Well,
and that's expected
at this very low, because it's very low concentration. But didn't we see something eventually?
Yeah, right. We had to run it for let's see. We ran it for so this is the case where we haven't stimulated it, right? So this is the base. What we're simulating here is the basal release rate, which is really slow. So we have to run it for probably, I think we ran it for like 50 seconds or something. Yeah.
Okay.
There we go.
Yeah.
100 seconds.
We can see that there's with the very low, at the basal concentration, there's very little binding, synchronous binding. Oh, what I should look at is these, not this. But what, wait, why are these never? Oh, we don't see them because it just, this is in a case of where I don't have enough points that I've sampled. So even though they're vesicle release events, but I'm not capturing the channel activate, the sensor activations that gave rise to those. I have to like, we hit this yesterday too.
Yeah.
There's only one. I don't know, man. It should. This model is not acting quite as nicely as the other one that we had. It's not showing the activations. I don't know why. There's probably.
Well, so this is the basal system. We're not stimulating it.
I know, but we should still. I do only simulate. How many complexes did I do here? 70. So that's the same. We definitely.
But the activated ones, Jim, the activated ones will only exist for a fraction of a millisecond because of gamma. You're counting the active ones as being the ones that are fully bound and have a docked vesicle. But as soon as they get activated, they will release their docked vesicle. So they'll disappear at rate gamma, which is, thousands per second. So you won't see it in the activated state, I think.
Oh yeah, I mean I know we saw.
Yeah, it was coded slightly differently in the other version of the model, I think.
It would take some more. We're pretty much at the end of the time that we, the 2 hours, and people must be getting tired. I don't know how many people are left.
I think we're all here.
So maybe you can show the results from the second model.
Sorry, from this one?
Yeah, maybe jump to that one as showing what we want to show.
I don't have the. Okay. I'll show that in just 1 sec. Let's just go back to the plot that I had here for 1 sec. And so, I mean, we do see that sometimes there are release events. This was.
I think the thing to look at are the release events. And for the validation, what we want to compare to is, I don't know, figure 2 from the paper or whatever it is, which shows the basal release rate, which is about one vesicle every 10 seconds. Figure 2, panel A.
So,
and you would need to run more instances to get a good smooth slope for this line, so we could estimate the slope of this line.
Yeah, so we can do that a little bit. Did I just close it? I just closed. Thankfully, it's good. I know it's going to come back up without too much trouble. The thing was, we did all the simulations with the basal state, and then we started doing the
stimulus.
The stimulus.
The action potential.
And and then I don't have the ones.
Well, I think it's easy to turn off the action potential though.
Yeah. It's just. That was the old one.
There it is.
It's a little bit unhappy but here so here we have, I'm obsessed with, do I see any, there's something, I screwed this up.
And I think the reason is the reason I said. Those are only going to persist for a fraction of a second.
We saw them before though.
But I don't think you counted them that way. I think you counted it a different way.
Oh, that's not what I want to change. What I want to change is.
Yeah. whether they have a dock vesicle or not.
This is making me very
That's gonna
paranoid about my model.
That's going to help.
You don't want me to be anxious, Tom.
I'm sorry.
Here, let's try this again. I don't think, yeah. I mean, I think you're right that that's the confounding factor. So we don't see any, no, something else is wrong.
Yeah, still not seeing them.
I know, because look, there's tons of release.
We're getting the releases, yeah. And
It's
that looks
working. The
correct.
model is working, but I've done something. I just don't know. I'm really puzzled by that because we literally use the same observables. The net file. Let's see what's going on. So the observables get turned into these so-called yeah, okay, this is annoying too. Oh, I see. Yeah, the observables get turned into these the group block, and the way that works, the multiplicity. So the species index is the second number, where it's a comma separated list of species indexes that can be modified by a multiplicity factor. Here it's 120 because of combinatorics. It's weighting each of these by a factor of 120, which is even more, all the more reason to be surprised by the fact that you never see these species being populated.
Yeah.
But there's 1, 2, 3, 4, 5, 6 species that correspond to the full synchronous. But there's and then there's 1, 2, 3, 4, 5, 6, 7. What are these? Like, so 38. What species 38? 38's got everything bound. So yes, clearly both of those, but docked vesicles 0. So and then there's 19.
Right.
Docked vesicles 1. And so both 38 and 19 should be down there on our list. And 38 is there, but 19 is not there.
Oh.
It's almost like I don't know why that is happening. Wait, what happened to that file? This is that's just something slightly mysterious. Why that? It's which, like I said, it's puzzling because clearly the model is working somehow, but we should be getting these guys, something happening with these guys, but they're not. Well, I said, yeah, this was this was the old this was the observables are being defined the way I thought they were, not referencing docked vesicles.
Right.
And it's missing the states that have docked vesicles. Still, it's not counting them. Don't know why that should.
Oh, maybe you have to say DV. Well, yeah, by not mentioning DV, that means it doesn't care.
It shouldn't care.
Right. So it should be included.
Oh, I was wrong about state 19 though. Okay. 7. Oh, here's, no, I see, it's 35.
35.
That's what 35 is there. Okay.
There it is. 35
So
is there.
yeah, the other thing to look at, we can plot all of these. We'll see how I see it turns. Yeah, none of these is getting populated.
Huh.
So I'm not sure exactly what has gone on wrong here, but this is what happens when you depart from. It's like all of these are 0. What is going on? That's obviously S6 is the into this file. S6 is v release, right? And no. This is the CDA, okay. But why did it? Practically the only thing that was not 0 is the release and S5, which is the empty. I don't know. This is something very weird is happening here. I don't think it's the model is wrong, but well, yeah, I see some errors up there, but yeah, I don't know. Well, I'll have to do a little bit more debugging and post a full version, a corrected version before, as soon as I can get that up there. The other thing, I guess the other thing I can mention here too is Tom and I did work out a completely different way of encoding this, which is also worth having a look at. And what I'm just gonna show it real quick, that because we were alluding to this and I've shown flashes of it before. This one, we encoded the sensor using 2 different molecule types that we linked together. So there's the site 1 and site 7, and then we made them form a complex. And instead of modeling the calcium binding explicitly, we just modeled it as an index. So the component state took on values 0 to 5 for the synchronous and 0 to 2 for the asynchronous. And we encoded that. It takes more rules. So for each binding event, you have to increment the number that are bound by 1. So we encoded these a little bit more explicitly. I didn't have to use the local functions. You can see how I put the multiplicities in manually, 5, 4, 3, 2, 1, and then the cooperativities, I put those in manually also, 1 to 5, multiplicities 1 to 5, and then B 0 to 4 for the dissociations. And I did the same for the asynchronous. So this is also still a very concise way to encode the model. And then and then the vesicle release and the vesicle docking was very similar. And the other thing that we did in this model that I was playing around with, we created it. There's no explicit time variable in BioNetGen, but you can create a time variable by having a constant rate reaction, a 0th order reaction that just produces, here we call them ticks. Typically, we set the tick density to be something, so that you get ticks produced at a rate that's higher than the time resolution that you want. And then we use the ticks observable. We created an observable that counts the number of ticks, and then we can use that as a clock variable. It's not the prettiest way to do things, and there's alternatives. There's an alternative way to do time-dependent functions, but it is pretty flexible. So we use that to make 2 Gaussian pulses, 2 Gaussian calcium pulses, and that does seem to work. We got this model to run and give some interesting results. So if we just look at the calcium, so we see that we have 2 pulses of calcium flux here, and then we can look at the profiles. I think I ran this model ODE, huh? I think.
You just ran it.
Yeah, it's actually instructive to. It doesn't. The stochastic version is not. It's funny that it resets the view when it shouldn't have done that, but okay. So these are the pulses, and then the snare. We can see that most of the activity when we have these large, quick pulses of calcium come from the synchronous form, and you can actually see. I don't think you saw this before, Tom, but you can see the pulse pair facilitation here. So like this peak is like 2.5. Oh, it's actually not. It's actually the opposite here. Oh no, I think if you so this is about 2.5. But this one goes from like 1.3 up to 4.3, so it's almost 3. So you can see that the number of snares that's activated in the second pulse is greater than the number from the first, and you can also see that in the vesicle release. So the height of this second jump here is greater than the height of the first jump. We didn't quantify this, and it's tricky, right? Because they're spaced closely enough. It's not clear where you should stop. What you should count for the heights. I'm not 100% sure how you'd want to do that, but this model is definitely working correctly as intended. We also ran stochastic simulations of the same thing. Oh, that's still the ODE one. Here's the stochastic one. I don't remember. This pulses might be different than for this one. I don't remember exactly what the conditions were here. This is the calcium. Let's see. Yeah.
Well, and you can see because of the stochastic nature of
that,
right?
First pulse is a little bit more robust than the second one.
Right. Yeah. Exactly.
For just because of randomness. So
right.
In order to really calculate the effects of each of the pulses on an average, you'd have to run an average of many simulations, which you can do. That's an example of a nice application for the notebook interface that Sinan introduced, that you can very easily script to run, a large number of simulations, and then average them together. So the model the other model should give identical results to this one, and there's some tweaking that we probably need to do to make that work. But I will post this model as well, so that you can see both ways of encoding. Yeah, this is the pulse one, the base one. This was the original, yeah. Any other questions? So that I called it in the repo that I made, I called it snare 2, and I will push this. Beautiful. All right, everyone. I think that pretty much wraps up for what we were going to do today. Lots more stuff that we can explore and come back again, and we'll do some more. When I say come back again, next year. I think we're going to try to do in the coming year some more advanced sessions as well. I think they're really useful for showing people things that are tricky even to fully document in terms of how do you work with different kinds of models and encode features of different models. There's usually a tricky, there's usually a way to solve most problems that you will encounter, but explaining how to do all of the different things is a challenge, I would say. All right. So there's another session coming up at the top of the hour. Is that the plan?
Yeah. I think
On Cell Organizer.
On Cell Organizer. So people have no time for a break, but I think we.
Yeah, I mean, depending on.
Start promptly at 10.
I don't.
Okay.
People are asking if it's virtual. I haven't. Yeah. Okay. Yeah, we don't have a plan. I mean, yes, but it would be nice to have some stuff that's in person, that's hybrid in the future too. There's no substitute for sharing your screen and having people be right up next to the screen that you're working on, though, as opposed to having to sit and watch it from the back of a room. That is.
Yeah.
Yeah.
I think this virtual way of teaching is really pretty efficient. All in all.
Yeah. I mean, what's sad is not meeting people in person, and there's lots of all the chit chat, which actually so often you find out, oh, we're working on a model of something that's very similar to that. Maybe we should collaborate. So those kinds of interactions are harder to have on Zoom.
Yeah, a little bit.
I want to thank Michael. Michael always has the best comments in the chat. I really appreciate it's like little boosts of energy, like, oh, someone is really enjoying this. Great, that's fantastic. I feel so good. I'm gonna keep going, even though I'm like, I've run out of gas. So it's really nice to have people out there.
What I lack in like fundamental understanding, I make up for in enthusiasm. So.
As I was preparing for the session this morning, I was like trying to remember how to write for loops in Python, so we all have our things that we know well and things that we forget or haven't learned yet. So no worries. Same thing like the neuroscience stuff is I'm not a neuroscientist, so I know the biochemistry and I understand that well, but how that plays out in in different contexts, there's a lot I don't know. So
Yeah, but
yeah,
that's the point of learning how to use all this modeling stuff. It's just to learn everything a little bit better. So it's a big process.
Yeah.
it's really cool to see how these mechanisms like the cooperativity that we started to talk about, how it plays out in, very sort of profound ways in this functional context, right? Like I don't know exactly what features of the of the response of the basically LTD, LTP it affects, but I'm sure that it affects the dynamics quite a bit.
Yep.
It's interesting. I mean, I didn't look at the original models, how they came up with that parameter B, for example, and
Yeah. So
whether how much tuning they actually did, or they just found something that seemed to explain their data.
yeah, I think it's really something that more explains the data. So there's a lot of history to the study of vesicular release that goes back to the 1940s and 50s, right? Kind of early days of neuroscience. And at one point, there's a famous paper from this these two guys, Dodge and Rahamamov, who I can't remember the date, maybe it's 1957 or something like that. They showed that the Hill coefficient of release is about 4. So at that idea, when that happened, the idea came about that whatever this calcium sensor was, it has to bind 4 calcium. But Hill coefficient, the relationship between Hill coefficient and the number of binding sites is only, especially when there's cooperativity and stuff, gets to be a little bit.
Well, you only have a Hill slope of n for an n site model if the cooperativity is, if you're in the fully cooperative limit, meaning it's all
right. Right.
Everything
exactly.
else is going to be sub
right.
less than 4.
Yeah, exactly.
Or less than n.
Or less than yeah. So then jumping forward in time quite a bit, we come forward to in the 1990s, Erwin Nair, who Terry talked about. So this is all appropriate because we started the workshop with Terry telling the story about how Erwin Nair, after he won his Nobel Prize, was invited to meet the Pope and asked the Pope, and the Pope asked him, if you could ask God anything, what would you ask, right? And his question was, what are the calcium sensors, and how, and what are they for, and where do they work? And he was thinking specifically about the calcium sensors in the presynaptic terminal that he studied. So in the 1990s, he published a paper with his graduate student or postdoc, Schneggenberger. So there's a paper, Schneggenberger and Nair, I think it's 1994 or 97, I can't remember, where they studied the synapses, the vesicular release in the synapse in the hair cell in your ear, and this is called the calyx of Held, H-E-L-D. It's a famous neurosynapse in your ear, and those synapses have to carry the stimulus away from the hair cells on your auditory nerve to your auditory cortex, and they have to go at about 1,000 pulses per second. It's one of the fastest synapses, and they have to be able to keep up with this rate forever. As long as there's sound coming into your ear, there better be signal coming out of your ear, or you'd be deaf, right? And so they just have to have this ability to transmit like crazy. So studying that synapse, they were able to use all kinds of different techniques to study how is it that how many vesicles are there, how are they fusing with the membrane, what's their sensitivity to calcium, how does it vary with the voltage, and all this kind of stuff. And studying that synapse is where they were able to come up with this very detailed kinetic model of the calcium sensor there, and see that there's this synchronous release and asynchronous release that occurs, and come up with the first really solid version of a model for what's going on there.
I don't remember. I don't remember if I asked you this question before, but what do the synchronous and asynchronous refer to?
Okay. So this is alluding to, this is getting back to alluding to what I was trying to, or getting back to what I was trying to allude to earlier in Jim's talk, right? So synchronous and asynchronous. So there's a paradox here. So synchronous refers to that the release is synchronous or phasic, right, with the transient of the action potential. That's what synchronous refers to. I mean, it's in sync with the stimulus, right?
Okay.
And asynchronous means it's desynchronized from that, or you can get releases at other times, right, that are less correlated with with the action potential, right? But what's a paradox here is the asynchronous ones only need to bind 2 calciums to make them release, and the synchronous ones need 5 calciums to make it release. So you think that the probability of getting to the 5 bound state is going to be way lower, so that should be the asynchronous one, and the one that only takes 2 calciums, that one should be very tightly coupled to the action potential because it only takes 2 to make it go, and that one should be the synchronous one, right? So what's going on? Also, furthermore, the affinity, if you look at the rate constants, you'll see that the off rate, right, for the asynchronous one is like 1 every 13 per second for the first binding, and 1/4 that for the second binding. So you would think that that one's going to have high affinity, and it does. That one is the high affinity site, and so if it's high affinity, that one should also be very well synchronized with the transient because it's high affinity. And the synchronous one takes 5 calciums, and that one is very low affinity. The off rate for that one is really high, right? So that one's low affinity, right? So how can it be? How can it be that the one with 5 bindings is the one that's synchronous and the one with 2 that is asynchronous? And the issue is resolved when you realize that affinity, the calculation of affinity, or the meaning of, or understanding of the importance of the affinity, that only comes into play at equilibrium. So the affinity is just a ratio of the off rate divided by the on rate. That's affinity, right? And it's just a ratio, and that ratio only tells you something meaningful, useful at equilibrium. During a transient, it's really the on rate that's the most important factor. Early in the early moments of a transient, it's the on rate that dominates. So the on rate for the synchronous sensor is really high. So if the on rate is really high, why isn't that one the high affinity one? Well, it's because the off rate is super, super high, right? To keep it low affinity. That means it's a high pass filter. It can only see very brief things because it's tuned to be a high pass. And the asynchronous sensor has a really low on rate. But wait, it has a high affinity. How can it have a high affinity if it has a low on rate? It's because the off rate is even slower. It's super slow off rate. So it still has a high affinity. It's tuned to be a low pass filter. And so in this snare complex, we have this kind of dual action happening where there's a notch filter, kind of a high pass notch filter, and an extreme low pass filter in the same molecule. And so what's all this about? Why do we have? So yeah, it's easy to understand the synchronous release, why you'd want to respond to the action potential, because that's what the release of synaptic vesicles or neurotransmitters supposed to be about. You have an action potential, boom. Here's your neurotransmitter, right? Except it's not really like that, is it? It's for every action potential that arrives, you only get release about 20% of the time. This, we would have shown that in the model if we had more time. But in the paper,
we should. I see that Ted is that the next presenter is stuck in the. I think we should get off.
Oh, okay. So that's the brief story.
Yeah.
Of what's going on there.
Let's vacate the premises.
Okay.
Well, yes, thanks a lot, Tom. I think that's all very, very instructive, and it was fun to play with this model.
Sure.
All right. See you guys later.
Sorry to interrupt you.
We're going off.
Sorry
it's going
to
to be on a
interrupt
different
you.
panel.
Excuse me. Hi.
Go ahead.
I need to leave this room. I have to make Caleb main host because I have to open another Zoom for the other group. So, is that okay for you?
Yeah.
We're out of here.
You were leaving. Yes, we noticed that Ted was asking about that.
Sure.
Okay.
See you later.